Welcome back to the StackIt series. There has been a long break since the last video, but actually I recorded 2 videos in between, but I didn't launch them because I thought the content was not very good and it was quite confusing what was happening. One thing that I will not make an extra video on anymore is that I developed some front end for our game. This was mainly to share it with a couple of friends, so I set up a simple Flask environment and some roots. I'm not particularly good with HTML or CSS or something, so it doesn't look very pretty, but this is basically the game. Let me just set this to 2 so we can play against alpha beta. It outputs the thinking, the performance, the lines that it found. So I actually deployed this one on DigitalOcean. Maybe you know it, maybe you don't. It's actually a quite nice service where you can get your own server for quite cheap, I feel. So this was one thing that I did. Initially I had a video on this, but then I kept stumbling over my own words, and actually in terms of how jQuery works and CSS works, I had to look up lots of things. So I won't do this now, maybe in the future when I'm prepared a little bit better. The next thing I did is I made a video on how to implement our board in NumPy, because for a long time I keep saying, oh, we're going to implement this in NumPy and it's going to be so much better and blah blah blah. I actually want to show how I went about this, and then I want to talk about why it was actually a waste of time. So first thing I did is I actually was interested in seeing how well are we performing. So one thing we can do is we just run our Monte Carlo tree search, which uses our board for 10 seconds, and we see how many games does it actually run on. You can run this a couple of times to get a better estimate. Maybe we'll do this, I'm not sure, but like we run in this particular position for 10 seconds and we see we get 3,200. If we run it again, maybe we get something like 3,600. I've seen before. Whatever, 3,500. Yeah. One thing you might notice is that the performance output, not the line out, I don't know how to call this. The output of our Monte Carlo AI changed a little bit. This is due to the front end, made it easier. So what I first did is I was curious, okay, if we check out in Monte Carlo tree search, what's the best move, where do we spend our time? So if you don't know, there's a tool called Line Profiler. Just search for it, you're gonna find it. And then you can do something like you can annotate your functions with add profile. And then let's go here and run simulation add profile. And then instead of running Python Monte Carlo tree search, we now run, let me just check somewhere here, a tool called kernprof with the -l parameter. Maybe -v would actually be the output that I was looking for. But anyway, so this will run your tool and profile the function that we just annotated. As you can see now, we only run 900 games. This is a lot less than before, but this is because it's monitoring all of those functions. And then I have to run this. I'm going to show the command python-m line profiler, and this file Monte Carlo lprof is what the output of kernprof is. So here you can see it wrote the results here. And if you run this, you can see for the annotated function, you can see each line. How often did we run in this line? How much time did we spend here? How much time did it spend per iteration? And what's the percentage of the total time? And in our getBestMove function, you can see that 99% of our time is actually spent in this run simulation, which is good. So that means that we don't spend any big other time, which we don't want. And if we go into run simulation, we can see, okay, it takes us about 9% of our time to generate the possible moves. 4% of the time to generate the string representation of the board. And you can see we hit this like 40,000 times. So the rest is clear, but the biggest chunk we can actually speed this up is 70% of the time is spent in board move. This is interesting to know. So in the last video, which I just mentioned that I didn't publish, where I was about to implement the numpy array, I also went into board. Let's go into the board and let's see where in our move function do we actually spend all our time. And just run this again for another 10 seconds. Okay. This is our move function, and you can see that 80% of the time is spent in deep copy of the board to append it to the history. And the rest is negligible. I mean, self throw over, this throwing over takes some time. Yeah, what should I say? So this is obviously garbage because like creating the history, especially for Monte Carlo tree search, we don't ever call undo. We just copy the board initially and we just run until the end. So we can fix this. In the last video, I decided not to fix this, but to implement the numpy version. And I'm gonna now show this, git reset hard, whatever changes I had, and then, okay, your branch is ahead. Yeah, this is good. So now in the master branch, I already committed this array board, which is my numpy version. And if you look at the code, some stuff got a lot cleaner. So, initializing the board is now a two-dimensional x by y numpy matrix. We can actually remove lots of loops by calling numpy.where, numpy.sum, whatever. And our move function also slightly changed. We only need a move function now, whatever. I implemented this, and then I found it was not faster at all. It was even slower than the previous board implementation. And what I learned is that actually element-wise access in NumPy is quite expensive. So if you do something like board 0 yx equals 0, and then you increase this one, then what it has to do is it has to somehow read this from a C array into Python memory. It has to wrap it into all the Python objects, compare it to the Python 0. Then here it has to do the same thing again and increase this value and write it back into the C array. So all of this is actually slower than the NumPy, no, than the regular Python board. So then I thought, okay, cool. So this was some premature optimization, even though I like this code maybe a little bit more because, okay, some stuff is cryptic. Like why do we have a list, zip, reverse, np, where, whatever. But I like that I can let the libraries do most of the logic, actually. Anyway, going back to this code, I then thought, okay, we can work with this deep copy thing. And I took some ideas from the NumPy board while I implemented it. And the way I thought I can implement this is instead of taking a copy of the full array, I will only always store the place where we made a move and what was the value and the player before. And this is like an easy access. Then instead of having this while loop with a throw over function, I know that if I have a 5, I will decrease it to be a 1, and then what actually happens is that I move on the neighboring fields, and then I know that inside this move function I have to check if this throws over 2, and so on and so forth. So this is now a recursive function which basically it moves on one spot, and if it falls over, it moves on the 4th spot next to it, and then if they fall over, it does the same thing, and so on and so forth. And then the undo function, instead of copying or replacing the whole arrays, I only have to replace the fields on X and Y for all the values in here. Anyway, if you're interested, you can check this in your quiet time. And then what we have here, do I want to show this? Maybe. Okay. So let's do this one. Let's remove this one. I don't know why this was committed. It's not yet pushed. So, okay, let's just run show perf true. This is not the same. So up here we have the numpy board, and down here we have the new board with the optimizations in place. So this is now running 10 seconds on numpy. Use the same field. What I like here a little bit is that actually, you know, there's some, oh, index out of range. This is actually something I noted on my list. So sometimes it seems to happen that in this run simulation, we do not have a next move. And now, of course, this is the effect when you want to show it on camera. It always happens. This is actually an error that sometimes happens, and I have no idea yet why. It seems to be happening sometimes. So I have it on my list to track down what happens, why there's no next move, but I haven't come around. So you can see, even with not profiling on the numpy array, we have like 860 moves. While now with our normal board implementation, the alpha beta stuff, with our normal board implementation and the removal of this deep copy stuff, we get 7,000 instead of 3,600 something. So this is actually, I think, quite a big improvement. And now if we check the move function again with our current profiler, let's immediately do this too. In the same time, we do almost twice, actually more than twice as many games. You can see even with the profiler, it does now almost 3,000. Before it was only 800 something. So let's check. If we now check the move function again, you can see that, okay, 5% of the time is actually spent in checking whether a variable, a Boolean, is true or not. Or appending something to an array, or checking whether a value is 0. So this is like something we cannot optimize any further, I guess. At least not in Python. Maybe we can remove function calls or something like this, but this is so low level optimization, I don't want to go there. So I think we optimized this board as much as we could. This will of course also benefit our alpha beta engine. So this was what I was busy with, and actually procrastinating on the, I always say fun stuff, but the fun stuff is actually taking a little bit longer than I thought. So I've been reading up on how AlphaZero works. I'm actually very interested in implementing it, but there's still a couple of things that I'm not entirely sure how they are implemented in detail, and maybe I can explain what I understand so far. Then I will read up a little bit more, otherwise, you know, I'm just stuttering during the video on, oh, now let's do this and maybe not, or whatever. So with AlphaZero, what we want to do is we want to run Monte Carlo tree search, but instead of, where is it? We are in get best move, we are going to be in run simulation. 1 second. Yeah. In this run simulation, in the phase where we decide which move to play. Here we do random choice, and here we do use this UCT or upper confident bounds, UCB, where we decide to take a move which seems more promising more often. I think all of this will actually be replaced with a neural network which will tell us, hey, we should play this move with the highest expected reward. And then after we finished expanding, I think instead of continuing to play until the game is done, what they do is they have another output of the same network which gives the probability of winning in a current board state, and then they just use this. Then instead of incrementing the wins by 1 or 0, they increment it by the probability of winning in this situation. And then they let just the network play against itself. I'm not entirely sure how the final reward is actually set. So once we know who won the game, how do we backpropagate this information in terms of a reward? I have to check that. So probably they do something like they go through every sample and set the probability of winning to 1 or something. I'm not sure. So this is something I have to read up on. Another thing I thought I might want to actually experiment with is here we have one big loop which first expands nodes, and if expanding is done, it just still keeps playing until a winner is reached or until we reach the max depth. And maybe this leads to some games where in the lowest node here we only have one play, and either we won this or we lost this or something like this. And I would want to make this so we separate expanding from play out, and then maybe once we are done expanding, instead of just running one game, we run 3, 4, 5 games or 10 games to get a better statistic on every leaf node, because currently the leaf nodes only have one game and it's not very helpful. 2, 3, 0, 2. Why? And so far I'm also not very happy with our algorithm. So our Monte Carlo tree search here says, oh, 2, 3 is a move where I win 55% of the time. And I would play 2, 3 and my opponent would play 0, 2. If we look at 2, 3, so red would play here, and then green would play here, and red would play here, and green 1, 2, and green would play here. Why would green do that? Green would never do that, because if red plays twice here, then this field is a 4, then green would throw this over and basically win everything. So, not convinced. I think we're not going to do much more in this video. Let's keep it a short one. Maybe one thing that I'm curious. Max depth. Let's just go here. Give it 30 seconds to find something. And only 10, look ahead 10 moves. Let's see how this works out. According to alpha beta, the best move is to throw this over. So, which makes sense. It would capture this one and would build a 4 here. So even if green tries to play here to throw this stone over or something, like this is just not going to work as a plan. Now we have 50,000 games. We played 13,000 of those 50,000 games here, and we have a 51% chance, and it's 3-0. Okay, this is actually what we want to find. It will be topping over, and then 2, 3. So green will take this one. Yeah, why not? And then we place 3-0 again. Why would we do that? Naja. Okay. Anyway. Thanks for watching. In the next episode, we're gonna start with Alpha 0 algorithm on StackIt.